Yeah, this album is dedicated to all the teachers that told me I never amount to nothing. To all the people that live above the buildings that I was hustling for that called the police on when I was just trying to make some money to feed my daughter. To all my peoples in the struggle, you know what I'm saying? It's all good, baby. It was all a dream. I used to read Word Up magazine, Salt and Pepper and Heavy D up in the limousine, hanging pictures on my wall. Every Saturday, rap attack, Mr. Magic Molly Mall. I let my tape rock till my tape hop. The bamboo sipping on private stock. Way back when I had the red and black lumberjack with the hat to match. Remember rapping Duke? The hard. You never thought that hip hop would take it this far. Now I'm in the limelight cause I ride tight. Time to get paid, blow up like the world trade. Born filler, the opposite of a winner. Remember when I used to eat sardines for dinner? East the raw G, Lucy B, Kids
everyone.
the shots like fuck start ski. I'm blowing up like you thought I would. Call a crib, same number, same hood. It's all good. And if you don't know, now you know. I made the change from a common thief to up close and personal with Robin Leach. And I'm far from cheap. I smoke stuff with my piece all day. Spread love, it's the Brooklyn way. The more weight and Alizé keep me busy. Girls used to diss me. Now they write letters, they miss me. I never thought it could happen, this rapping stuff. I was too used to packing gats and stuff. Now honeys play me close like butter play toast. From the Mississippi down to the East Coast. Condos and Queens. For weeks, sold out seats to hear Biggie Small speak. Living life without fear. Putting 5 carats in my baby girl ear. Lunches, brunches, interviews by the fool. Considered a fool cause I dropped out of high school. Stereotypes of a black male misunderstood. And it's still all good. And if you don't know, now you know. Super Nintendo, Sega Genesis. When I was dead broke, man, I couldn't picture this. 50-inch screen, money green, leather sofa. Got 2 rides, a limousine with the chauffeur. Won't feel about 2 G's flat. No need to worry, my accountant handles that. And my whole crew is lounging, celebrating every day, no more public housing. Thinking back on my one-room shack, now my mom gives an act with me on the. And she loves to show me off, of course. Smiles every time my face is up in the store. We used to fuss when the landlord dissed us. No heat, wonder why Christmas missed us. Birthdays was the worst days. Now we sip champagne when we Thursdays. Damn right, I like the life I live. Cause I was projected as the positive and the soul. And if you don't know, now you know. And if you don't know, now you know.
I see.
Yeah.
All right, how are we doing? Questions? Questions while we wait? Got another minute or two. How are we doing with trees? Questions, anybody, while we're waiting? No? Yeah, go ahead. Yeah. Go ahead. I mean, if we haven't seen it yet, but if it's stuff we've seen, you can go ahead and ask. Yeah, we haven't done that yet. We haven't done that yet, but let's wait until we do that. But today we're going to start counting arguments. And that's what that is. It's a counting argument. You know, this is why I don't like to open WebWorks too quickly, because some material we might not have seen, and then it just confuses everyone. But, you know, I mean, we are running out of time, so I have to kind of open up the WebWorks a bit faster now. There's going to be one more, and that'll be it, I think. All right, let's get to work. What we want to talk about today is Bayes' theorem, which gives us a nice relationship between probability of E given F versus the probability of F given E. No updates yet. So I mean, it'll be next week. So we have a nice theorem which relates these two things according to trees. And well, you know, I mean, first let me state it. Let me state it, and then I'll give you the proof essentially via trees. Bayes' theorem. What does Bayes' theorem say? Let F1 all the way to Fn be mutually exclusive events where the whole sample space is the union of those events. And let E be an event then the probability that some event Fi occurs given E, right, so this kind of thing is going to be written in terms of this, is the probability of E given that Fi times the probability of Fi divided by is given by this. And let's Let's prove this via a tree diagram. I mean, kind of difficult to understand what's happening here, but what are we saying? S is made up of all of these fn's. So you see what right? I mean, what can happen? Either F1 or F2 or F3 all the way to Fn. These are the possibilities from the sample space. And now, either E happens or not E in each of the branches. And so on and so on. Right, and let's associate some probabilities with that. What's the probability of F1 happening? Well, it's exactly that. It's the probability of F1. And then this is the probability of F2. And so on, the probability of Fn. And what is this? Here, let's put some probabilities there as well. Well, that's the probability of E occurring, given that F1 has already occurred. So this is the probability of E given F1. And here, this is going to be the probability of E given F2. And so on, probability of E given Fn. And then, well, I mean, of course, this is just going to be 1 minus that probability, and 1 minus that one, and 1 minus that one as well. But really, what are we interested in? The probability of Fi given E. So, right, I mean, it's a conditional probability, so it reduces the sample space to E having occurred. So you're in all of these branches, and what do we want? We want the ith branch, right? So the ith branch here, Fi, and then you either have E or you don't, with probability of E given Fi. So this is the branch you want, and being a conditional probability, you have reduced the sample space to all of these branches. So the probability of this branch happening is the product, right? P of Fi times this branch. Divided by the sum of all the branches. So P of F1 times the probability of E given F1 plus, and so on, all the way to Pfn times the probability of E given Fn. That's the probability of Fi given E. Very nice. Let's take a few examples from the book. we are given two events, M and N. The probability of M occurring is 0.4. Probability of N given M is 0.3. And the probability of N given M complement is 0.4. We are asked to find the probability of M complement given N. Well, I mean, we have options here. We can draw trees, right, as in the proof of Bayes' theorem, or just use Bayes' theorem directly. I mean, it's really up to you. I like to draw trees because, well, there's almost no thinking. What's the probability of M occurring? I mean, you're either going to have M or you're going to have M complement. The probability of M occurring is 0.4. So the probability of M complement occurring is 0.6. And then either you're going to have N or its complement. But what's the probability? What's the probability of N occurring if M has already occurred? Well, probability of N occurring if M has already occurred, that's 0.3. And you know the branches have to add to 1, so that has to be 0.7. And the probability of N occurring if M complement has occurred, well, that's 0.4. So again, the branches have to add to 1, so that has to be 0.6. Thank you, Amy. And now what do we want? We want this. Probability of M complement occurring given that N has already occurred. So you see it's reducing the sample space to N having already occurred. So we're in one of these two branches, that's the new sample space. That's your new sample space. And what branch are we looking at? M complement given N. This is what we want. So this probability is that branch, 0.6 times 0.4, divided by the sum of the branches. 0.4 times 0.3 plus 0.4 times 0.6. So what is that? 24 over 36. That's what? 6? 6 times 4 over 6 times 6. 2/3. Is that correct? Thank you, Amy. 2/3. There we have it. If you wanted to use Bayes' theorem, right, without going through these, you could. You could observe that M and M complement are mutually exclusive. As, what's the definition of mutually exclusive? You know that it's the intersection being empty. Thus, by Bayes' theorem, the probability of n complement given n is the probability of n given m complement times the probability of m complement divided by plus probability of n given m times probability of m. That's what Bayes' theorem says. And of course, it's going to be exactly the same thing. N given m complement, that's 0.4. Probability of m complement, of course, is 1 minus 0.4 or 0.6. And that, I mean, that's again the same thing. And this, n given m is given as 0.3. And probability of m is 0.4. Exactly, I want to say, the same as we had right here. Absolutely. So, I think with trees, it's very clear. So I never really remember Bayes' theorem by heart because it's a lot of stuff to remember, but using trees, I think, is trivial. How are we doing? Let's take another example. Let R1, R2, and R3 be mutually exclusive events. Exclusive events. Probability of R1 occurring, 0.15. Probability of R2, 0.55. Probability of R3 is 0.3. Probability of Q given R1, 0.4. Probability of Q given R2, and probability of Q given R3 is 0.7. We are asked to find probability of R2 given Q. let me point out that they don't say, right? I mean, if you want to use Bayes' theorem, you really should be in a situation where R1, R2, R3 are mutually exclusive, but also the union is the whole sample space. Notice it doesn't say that here, but the probability of R1, R2, and R3 together does add up to 1, right? 0.55 plus 0.15, that's 0.7, plus 0.3 is 1. So really, R1, R2, and R3 together form the whole sample space. So probability of R2 given Q by Bayes' theorem, that's the probability of Q given R2 times probability of R2 divided by we have this. Right, that's exactly what Bayes' theorem says. You can do it with trees, and that's again precisely the answer you'll get. Well, I mean, it's not that you should not use Bayes' theorem. I mean, all I'm saying is it's a lot to remember. If you use trees instead, I think trees are easier to work with. But here I'm using Bayes' theorem directly. So that's precisely what Bayes' theorem says. And we have all this information, right? Everything is given. That's 0.2 times probability of R2 occurring is 0.55 divided by the sum of the products. 0.4 times 0.15 plus 0.2 times 0.55, and finally 0.7 times 0.3. So whatever that gives, if somebody wants to work that out, I'll let you do that. Even in the case where they don't add to 1, well, that's of course an issue, right? If you don't have a whole sample space, you want to be careful, right? I mean, so as long as the hypotheses of Bayes' theorem are satisfied, you're good to go. So Javier, if we want to answer your question, under which condition can't we use this theorem? Well, let's ask the question that Hasmo was asking, when can we use it? You can use it if the hypotheses are satisfied. So you need mutually exclusive events that altogether make up your sample space. So as Asma suggests, if they don't add to 1, then we're in trouble. So we cannot use it. Consider the following. Suppose you have 3 jars with the following contents. 2 black balls and 1 white ball in the first. So first jar, 2 black, 1 white, second jar. Second jar has 1 black, 2 white, and the third jar one black, 1 white. One jar is to be selected, then 1 ball is to be drawn from the selected jar. If the probability of selecting the first, second, or third jar are 1/2, 1/3, and 1/6, find the probability that if a white ball is drawn, it came from the third jar. If they don't add to 1, could you create an arbitrary event, right? The complement of the union of those 3, and determine the probability of the unknown. The issue with that, and it seems like the thing to do. You probably wouldn't know the probability of the event that you want to work out occurring in that fourth new thing that you just made up. You can, of course, calculate the probability of the fourth, absolutely, but not the event occurring in the fourth. That would be a big issue. You see what I'm saying? Right, and suppose you had, in this example, you had R1, R2, R3, and suppose they did not add to 1, right? So 0.4, 0.1, 0.2, 4, 5, 6, 7, right? They only add up to 0.7. So there's got to be something else with probability 0.3 that is not any one of those. So R1 union R2 union R3 complement the rest, essentially. But you have the probability of E occurring here as, right, whatever, or Q in this case. Probability of Q given R2 was 0. So probability of Q given R1, that was 0.4 again. And then it's either Q or not Q. Or Q complement. And then you've got Q or Q complement again. You have each of these things, right? This was 0.2. And this was 0.7. So you can calculate these things, 0.6, 0.8, 0.3, and now we're in trouble. Now we're in trouble because we don't know what these things are here. Right, and he suggests there may be more than 4, there may be 5, and so on, but they could all be grouped together as the complement of this business. And these would still be mutually exclusive. So that would be, I mean, it's very nice and natural to include this 4th business, but we have a big problem with figuring out the probability of Q occurring given that this has happened. It's not given. We're in trouble. It's not given, and there's no way of evaluating it. All right, consider this a very nice question, right? So 3 jars, first jar, second jar, third jar. Probability of picking the first jar is 1/2. Probability of picking the second jar is 1/3. Probability of picking the third jar is 1/6. What is the probability that if a white ball is drawn, it came from the third jar? In other words, what is the probability that it came from the third, given that it was white? So let's just draw a tree diagram. You could, of course, do Bayes' theorem, the set theoretical way, but we'll do it with trees. You're choosing a jar at random, so it could either be jar 1, jar 2, or jar 3. Probability of choosing jar 1, 1/2. Probability of choosing jar 2, 1/3. And 1/6. If you're in jar 1, probability of choosing white versus black, right? You've got 1 white ball and 2 black, so 1/3 versus 2/3. Probability in jar 2, the probability of choosing a white ball, 2/3 versus 1/3. And in the third jar, 1 black, 1 white, 1/2, 1/2. We are in a conditional probability, so that reduces the sample space. You know a white ball has been chosen. Is it relevant to write out the probability for jar 1 and 2? Absolutely, 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 because here, right, conditional probability reduces the sample space to having chosen a white ball. So you know that you're either here, there, or there. So both, all jars play a role here. Right, you know that the ball you chose was white. We want to know where it came from. What's the probability that it came from the third jar? So this is the branch we want. So probability of third given white, that branch 1 out of 6 times 1/2, divided by the sum of all the branches. 1/2 times 1/3, plus 1/3 times 2/3, plus 1/6 times 1/2. So 1/12, this is 1/6, plus 2/9, plus 1/12. So 36 has a common denominator there. Six plus 8 plus 4 over 36, is that correct? So that's going to be what? 12, 18. So 1/36 over 12 times 18. This is 2. 1/6? Is that 1/6? Anybody? Have I made a mistake? One over 6 seems to be the answer. 1/6, thank you, Thomas. All right. Questions? Let's try another one. Well, since we have this nice diagram, why don't we work out? Seems like a waste to just do the one question. Why don't we work out the probability that the ball, a black ball came from, if a black ball is drawn, what is the probability that it came from the third jar? Right, so in that case, you know it's a black ball, so it reduces the sample space to these 3 branches, and this is the branch we want. So what is that? That branch, 1/6 times 1/2, divided by the sum of those branches, 1/2 times 2/3, plus 1/3 times 1/3, plus 1/2 times 1/6. So that's 1/12. This is 1/3 plus 1/9 plus 1/12. Common denominator of 36 again. And this is going to be 12 plus 4 plus 3. 16, 17, 18, 19. So 19 over 12 times 36. Whatever that is. There it is. For the previous question, Javier got 3 out of 17. Have we made a mistake? Where's the 17 coming from? Common denominator was 36. So that's 6 plus 8. Oh, that's not plus 4. It's plus 3. Plus 3 plus 3. Plus 3. Thank you. So that should be 17 plus 3, right? There's a mistake there. And that is 3 over 17. Thank you. Is there a relationship between third jar given it's white and white given the third jar? Right? I mean so first there was a mistake, right? So this is the probability of third given white. And what is the probability of white given third? Right? What is the probability of white given third? Well, if the third, this has already occurred. That's what we're saying, right? It's a probability, it's a conditional probability. This has already occurred. So you're already right here. You know you're choosing from the third jar. What's the probability of getting a white? 1/2. Absolutely no relationship between the two things. Well, no relationship in this. I mean, there's no, but of course there is, right? In the sense that this can be viewed as, again, by Bayes' theorem, this is a probability of white given third times the probability of third over probability of white given first times probability of first plus probability of white given third times probability of third. Right, so there is a relationship in this fashion by Bayes' theorem. Bayes' theorem gives us the relationship between the two. It's not an obvious relationship immediately, but that's how they are related. Consider number 12. A building contractor buys 70% of his cement from supplier A. Contractor buys 70% of cement from supplier A. And 30% from supplier B. A total of 90% of the bags from A arrive undamaged. while 95% of the bags from B are undamaged. Find the probability that a damaged bag from, well, so what is the probability that a damaged bag came from supplier A? Right, so we have supplier A and B. You're buying 70% of the bags from supplier A and 30% from supplier B. If the bags from supplier A are undamaged, and from supplier B, 95% versus 5%, what is the probability that a damaged bag came from supplier A? In other words, we want a probability that it came from A given that it was damaged. What is that? Well, again, conditional probability, right? We know it's damaged, so we're already there. We want the one that comes from A, so we want this branch. So 0.7 times 0.1 divided by the sum of the branches. So that is 0.07 over 0.07 plus 0.015, so 0.85 or 7/85. No. What is that? All right, 70/85. Thank you. 14/17. Thank you, Annie. Brendan. There it is. Convinced? Have we done enough of this Bayes' theorem business? I think so. Let's move on. let's move on by defining, in case you've never seen it before, the idea of factorial. Did we define this in class already? Given a natural number n, we define n factorial denoted n with an exclamation point, n factorial, to be the product 1 times 2 times 3 all the way to n. There it is. We're defining n factorial as this product. So example, 1 factorial is the product of natural numbers 1 all the way to 1. Well, I mean, you're already there. This is 1. 2 factorial is the product of numbers 1 times 2 all the way to 2. Well, again, we're already there. This is just 2. 3 factorial, 1 times 2 times 3. Easily seen to be 6. 4 factorial, 1 times 2 times 3 times 4. Multiply these numbers out. It's easy to see that this is 24, and so on, and so on. You can define factorials for any natural number in such a way. Let me follow up that definition and define 0 factorial, because that happens a lot. It's not defined in this situation, right? Because we are restricting our attention to natural numbers here. But we're going to extend the definition to 0, and we're going to define 0 factorial to be 1. This is an arbitrary definition, but you will see that it's very convenient. So 0 factorial is defined to be 1. So now we're going to start some counting exercises. We're going to count how many things can happen. And let's start with a nice, easy exercise. Suppose you're playing Scrabble. Suppose you're playing Scrabble and you have 5 tiles. Each with different letters. So you've got 5 different letters here. Here's my question to you. So this is 5 different letters. Here's my question to you. How many 3-letter words can you make? And I use the word words here loosely. Right, because, and really what I'm asking is how many 3-letter sequences can you make? How many different strings of 3 letters can be made here? Right, I mean, it doesn't have to be an actual word in the English language, right? I mean, suppose you had A, B, C, D, E here. So, I mean, of course, you can make the word ace, and that's a very nice word. Everything's fine, but I mean, C, D, E would also be an acceptable word. So how many three-letter words can be made? Right, and you know, I mean, imagine each word has to have 3 different letters, of course, right? Because you can only choose from these 5 tiles. So, you know, I mean, you're looking at your board, you've got these 5 tiles, and you're rearranging them to form 3-letter words. How many can you make? How many 3-letter words can you make? Well, how many options do you have for the first letter? Right? You have to choose one tile from here. So you have 5 options. Once you've placed a tile as your first letter, how many options are left for the second? You see what's happening, right? You'll have only 4 letters left for the second option. And once you've placed the first and second letter, how many options for the third? 3. So you have 5 times 4 times 3 possible 3-letter words. Let's repeat. Let's repeat where instead of just having 5 tiles, suppose you have 26 tiles, right? 1 for each letter of the alphabet. How many 3-letter words can be made using the entire alphabet where, well, I mean, first let's just say this. How many 3-letter words can be made using the entire alphabet? How many letters in the alphabet? Well, we never know. "26." Thank you. So how many 3-letter words can be made using the entire alphabet? Well, how many possibilities for the first letter? 26. Once you've placed your first letter, how many possibilities for the next one? Still 26, right? There's no restriction here. It doesn't say that the letters have to be different. And for the third, 26 as well. So in other words, 26 cubed possible 3-letter words. Thank you, Annie. However, what if we now make a restriction? where no letter can repeat. So still, what was the restriction on the previous example? Well, we had 5 tiles, right? We were playing Scrabble. We had 5 tiles, each with a different letter. So you didn't have 2 tiles with an A, right? So ACA was not a possibility. Here, if no letters can repeat, as Annie suggests, right? You have 26 options for the first letter. But once that first letter has been set, you only have 25 for the next. And once those 2 letters have been set, there are only 24 options for the last one. So 26 times 25 times 24 possible 3-letter words where no letters can repeat. What's the connection of this with factorials? Right? I mean, factorials and factorial is 1 times 2 times 3 all the way to n. Or if you write it the other way, the decreasing way, n times n minus 1 times n minus 2 all the way down to 1. Here, you have 26 times 25 times 24. You're not going all the way down to 1. So it's not really a factorial. But I mean, what are we missing? We're missing 23, 22, all the way down to 1. So if you multiply by what you're missing and divide it by itself, right? Now the numerator can be viewed as 26 factorial, and the denominator is 23 factorial. Right? Compare this with 5 times 4 times 3. Not really a factorial, but if you throw in 2 times 1 and you divide by itself, so really you're multiplying by 1 here, you're not changing anything. And now the numerator can be viewed as 5 factorial, and the denominator is 2 factorial. Or 5 factorial divided by 5 minus 3 factorial. Here, 26 factorial divided by 26 minus 3 factorial. Definition. Definition, a permutation of R elements from a set is any specific ordering or arrangement without repetition of the R elements. Period. The number of permutations denoted P and R, or some books and or calculators, right? If you have a scientific calculator, you might have this button. So P and R, the number of permutations, n factorial over n minus R. Factorial, exactly what we've noticed that I've erased here. Let's convince ourselves, right? What are we doing? You have a set of n elements, n different elements, n letters, and you want to form a string or a word with R letters. Right, so R letters. How many choices for the first one? Well, you have n choices for the first one. Once the first one has been set, how many choices for the next one? N minus 1. Once the first two have been set, n minus 2 for the third, and so on, right? So first, second, third, if you have R of them, and minus, right, again, so first, second, third, so it's minus 1 less. You have R of them, so n minus R minus 1. And then if you multiply by 1, namely n minus R, n minus R minus 1, all the way down to 1, all over itself. The numerator is n factorial, and the denominator is n minus R factorial. There it is. How are we doing? Let's work out a few. What is Pn1? According to this formula, this is n factorial over n minus 1 factorial. Can we simplify that? What is that? N factorial, by definition, is 1 times 2 times 3 all the way to n. What is n minus 1 factorial? 1 times 2 times 3 all the way to n minus 1. Right? This is the stopping. This is where you stop. Let's go back to that numerator there. 1 times 2 times 3 all the way to n. What is the number before n? The number before n is n minus 1. And so you see what's happening, right? These cancel, everything cancels except n. Thank you, Annie. Is it? Thank you. Let's argue this a different way. What is this? This is the number of permutations of n objects taken one at a time. In other words, how many one-letter words can you make with n letters? Right? You're making one-letter words. So it's either the first letter or the second or the third. You have n letters, n words. Let's work this out. The number of permutations of n objects taken n at a time. Again, by definition, this is n factorial over n minus n factorial. Or n factorial over n factorial over 0 factorial. And we had defined 0 factorial to be 1. So this is n factorial. Does that make sense? Let's think about this. What is this saying? The number of permutations of n objects taken n at a time, or in other words, how many n letter words can you make with n different letters? Well, how many choices for the first one? You have n choices. How many choices for the second one? Once the first one has been set, n minus 1, and n minus 2, and so on, all the way down to 1. The product is n factorial. How are we doing? Let's take a few examples from the book. Page 380, number 14. A menu offers a choice of 3 salads, eight main dishes, and 7 desserts. Desserts, not deserts. How many different meals? how many different meals consisting of a salad, a main dish, and a dessert can be made? How many different meals? Well, you're going to have a salad, you're going to have a main dish, you're going to have a dessert. How many options for the salads? 3 options. How many options for the main dish? 8. How many options for the dessert? 7. So 3 times 8 times 7. Absolutely. Consider a club with 16 members. Right, you have a club with 16 members. How many ways can a slate of 3 officers consisting of president, vice president, and secretary be chosen? How many slates of president, of 3 officers, president, VP, and secretary? That's a question. Right, so imagine the scenario, you have a chess club or whatever, with 16 members in total, and you want to choose some sort of representation, president, VP, secretary. So Julia wants to know why product and not sum. Imagine the scenario. Right, I mean, so suppose you fix a salad. So suppose a Caesar salad. Caesar, I don't know how to spell Caesar. Chef salad. Right, so you fixed the chef salad, you fixed some main dish. What's an easy to spell main dish? Burger. And now you have 7 desserts. So you can cycle through those 7. And that will already be 7 meals. Right? And now, change the main dish. Change the main dish and cycle through those 7 desserts once again. So that's going to be another 7 different meals. And you can do that 8 times. So that's going to be, you're going to add 7, 8 different times. That's 7 times 8. And now cycle through each of the different salads. So you're going to get 7 times 8, 3 different times. That's why it's multiplication. Is that clear, everyone? It's a very important question. But there it is. And so this idea of why it's multiplication as opposed to addition generalizes to everything we've been doing. And now, let's propose a counting argument for this. You've got a club with 16 members. How many committees of 3 different people, including president, VP, and secretary? How many choices for the president? You've got 16 members, 16 choices. Once the president has been set, how many choices for the vice president? Well, I mean, you've set the president, there are only 15 possible choices left. Once these 2 people have been set, 14 choices left for the secretary. This is really the number of permutations of 16 elements taken 3 at a time. 16 times 15 times 14, or 16 factorial over 13 factorial. Absolutely. How are we doing? Questions? We have time for one more. Let's do one more. Number 20. Nah, that's enough. 20 is the same kind of thing again, so absolutely. How are we doing here? Practice these counting arguments. We'll do more next time. And next time we'll also ask the question, how would you use a permutation button on your calculator? I don't know. I suspect you might want to enter the number n first, then press on this button, and then enter the number for r. So I suspect in this case, 16, PNR, and 3. Try that. This is only a guess. I am not an expert on calculators. And if this is not working, maybe press on that, and they might prompt you for N and R, and that would answer the question as well. Right? I mean, that's the question. Javier is asking the good question. Does the order matter here? And does the order matter? And in this case, the order matters very much, right? Because it's not going to be the same slate if you're president or if I'm president. So here the order matters very much. But a very good question we're going to answer next time is, what if the order doesn't matter? What if we just wanted a 3-person committee where roles as president, VP, and secretary are not assigned? What if you wanted to ask the question, how many 3-member committees can you make? Also an excellent question, and we'll tackle that next week. Thank you all for coming. You guys have a good weekend, and we will pick this up again on Tuesday. You guys have a good one.